Welcome to this video. In this video, I will be continuing the proof of the previous discussion, which was basically to ascertain that how Holevo-Hellstrom theorem can be applied in subchannel discrimination task. So here I have written the theorem again. You can look into the previous video for the motivation of this theorem. So the state rho does not belong to a convex set F that I have shown here. If and only if there exist subchannel discrimination task epsilon 0 and epsilon 1 such that the maximum probability of success maximized over the POVM sets of the state is always greater than the maximum probability of success you can obtain from the states within the convex set. So this is the state within the convex set condition. So the main ingredient towards proving this will be something called as hyperplane separating theorem or separating hyperplane theorem, which is also called Hahn-Banach theorem, which basically says that I can have a observable W belonging to Hermitian operator that can observe the fact that my state is outside the free set. So basically here if I take this state rho, there exists a observable for which the expectation value of the state is always less than 0, but it is always greater than equal to 0 for all free states. So this means it's kind of cutting it into a plane where the upper part of the plane it gives a positive value, negative value, and lower part the positive value. So this observable will be different for a differently chosen state. So I can have different cuts. I can have cuts here. So this is the main idea of choosing W. But once the W is chosen, there always will exist a W that is guaranteed by separating hyperplane theorem. So there always exists a W for rho not in F, and it separates a sigma belonging to F. So now what we can do is we take this W and take the maximum eigen value of this W. So we call it W max and take the mode of this. This is also defined as the infinity norm of W. So this is the maximum eigenvalue of W, and what we do is we create another operator that is defined as identity minus W over this W max, which I call Wm. And now observe that this is always greater than equal to 0, because W over W max is something that is between -1 and 1, because W max is the maximum eigenvalue, and I can always form a spectral decomposition or the eigenvalue decomposition of this matrix W, which is a Hermitian matrix. So with this we define X, and we can again take the max Xm, the maximum eigenvalue of X, because X is now a positive semi-definite matrix. It also has a max which is strictly which will be greater than 0 hopefully. And now what we can observe is, observe 0 is always less than X over X max less than equal to 1, because I am dividing by the maximum eigenvalue. So this is first observation. The second observation is that because -1 W over Wm less than 1, it implies that 0 is greater than equal to trace sigma W over Wm less than equal to 1. This is one condition, and -1 greater than less than equal to trace sigma for this it will be rho W over Wm greater less than equal to 0. So these two conditions, they simply come from this condition here by multiplying it with sigma and rho and taking the trace. So here one must observe that we have also used the separating hyperplane theorem, which guarantees that the expectation value, which is simply a trace w row, is always less than 0 for row that is not in F, and it is always greater than equal to 0. So here you can see I have used the separating hyperplane theorem, and here also I have used the separating hyperplane theorem. And these this lower bound and this upper bound, they come from the point here. And with this we are ready to actually construct two channels, basically channels. Let's construct channels epsilon 0. These channels will be the channels which gives us the benefit in the task of subchannel discrimination. So if you want to distinguish between these two channels, a state that is outside the free states will always be helpful. So rho 0 of eta is defined as trace eta identity by 2 plus sigma z trace eta x over 2 times a maximum value of the eigen value of x. And similarly I have epsilon 1 of eta is trace eta I by 2 minus sigma z times this same value repeated again. So these are the two channels. These are completely positive trace preserving channels. So now the question is, they map any state, so any state in d-dimensional Hilbert space to a two-dimensional subspace. So this two-dimensional subspace can be spanned by some vector 0 1 which are orthonormal. Without loss of generality we take them to be 0 1 and give sigma z and identity to be in this subspace. So with this idea I will discuss one thing, why this is completely positive trace preserving. So the trace preserving condition is easy to see, because sigma z has trace 0, so identity by 2 has trace 1, so trace of eta is preserved. So this condition is simple to check. Now complete positivity is a bit tricky to check. It is always difficult to check complete positivity. First, positivity is simple to check. Positivity, it is simple to check because 0 is always less than equal to trace eta x over 2xm less than equal to trace eta over 2. So this holds because simply x is between, so this is positivity condition because 0 x over xm is between 0 and 1. So this condition holds, and this condition ensures positivity. This ensures positivity. And now for complete positivity, what you can do is you can check that I tensor epsilon I of phi. So this is the Choi matrix. This is the Choi matrix. This Choi matrix is a positive semi-definite operator. This is again easy to check. I leave it as an exercise to show that this Choi matrix is a semi-definite operator, and hence these maps are completely positive trace preserving. So now what we can do is we can calculate the probability of success using these maps, and this is simply half trace m0 epsilon 0 of rho plus half trace m1 epsilon 1 of rho. And now the maximum over all, so maximum over all m0 m1 is actually given by the Holevo condition, where the Holevo-Hellstrom theorem is applied to this and this operator. So that is given by Holevo-Hellstrom theorem. It is simply half 1 plus half epsilon 0 minus epsilon 1 of rho. So here we have done nothing but applied Holevo-Hellstrom theorem. So here is application of Holevo-Hellstrom theorem. And now what we can do is we can simply compute this value, because we have the explicit form of the channels, and this value is same as half 1 plus trace rho x over mod xm. So this is because epsilon 0 minus epsilon 1 is sigma z times this trace eta x over xm, and then you have to calculate the norm of that thing, but this is already diagonal, so you can just take the modulus values. So this will give you 2 times trace eta x over xm, but there is a half here, so the 2 cancels out. So now with this we are almost at the end of the proof. Now what we have to show is that for any state that is within the convex set, this value is always less. But this is apparent because now notice that what we have said is this particular thing, that this thing is between 0 and 1. This means 1 minus of this thing, which is particularly this quantity here, it will be also between 0 and 1. And similarly this thing is between minus 1 and 0. So 1 minus this thing will be always between 0 and 2. So with this what we have is, now notice that 0 trace sigma x, 1 greater than trace rho x for all sigma belonging to the convex set F. So what this means is that my trace rho x will always have a higher value than my trace sigma x, and that value will exactly be greater. So this means that PS will always be high. So let's write what this means. This means there exists epsilon 0, epsilon 1 such that max MIPS of rho will always be greater than max MIPS of sigma for rho not in F and sigma belonging to F. So this means that my state which is outside the convex set will always have a larger value because of this separating hyperplane theorem and the form of Holevo-Hellstrom saturation value. So that's all for this video. In the next video I will talk about semi-definite programs, and it will be a new idea. We will discuss how things like mean conditional entropy, robustness, these can be framed in semi-definite program, which plays a crucial role in quantum information theory.